So lesson 4.3, we're going to start talking about your trig functions and the unit circle. And yes, you do get to use your reference sheet here. I'm going to skip the warm-ups for the sake of time. But this, or something like this, is on your notes right at the top. These are the trig functions for any value in what you guys probably consider the coordinate plane, or eventually the unit circle. These are like the big kid versions of sine, cosine, tangent, cosecant, secant, and cotangent. So instead of saying opposite over hypotenuse for sine, they're going to start calling them y over r. And what those represent is something that, for me, makes a lot more sense. Because if you're in the coordinate plane, I like to think about coordinates, which I'm very comfortable with, right? We've been working in the coordinate plane for a long time. So you're going to have an ordered pair along a terminal ray. The ordered pair is called xy. And you can create a right triangle by connecting it to the closest x-axis. So you have an x value, you have a y value, and then the hypotenuse of your right triangle, the distance from the origin to the point, is going to be considered r. So you'll notice the formula for r here just looks like a really simple Pythagorean theorem formula, which it is. So you have to, I don't think these are on your formula sheet anywhere. Right? This box of formulas is not anywhere on your formula sheet? Okay. So for me, you know, with the dyslexia and all, sometimes I don't really rely on the formulas as much as my drawing. And that's saying a lot, because my drawings are terrible. So let's talk about, okay, I love her graphic here. The bow tie thought. So remember how I said the triangle has to connect with the nearest x-axis? So we're looking for triangles that are creating reference angles with the x-axis. So your only options for triangles are either this triangle, or this triangle, or this triangle, or this triangle. Obviously they're going to look a little skewed depending on where the point is, but oops, why did I do that? 4. That's not what I wanted to do. 4. There we go. So, remember the mnemonic device? You guys just developed the unit circle for me, so I know you do. All trig functions are positive in the first quadrant. Sine is the only positive trig function out of the major 3 in the second quadrant. Tangent, and then cosine in the opposite quadrants. All students take calculus is the mnemonic device that I use for who's positive and where. Is there another one? I feel like there is. I just never use it. Oh, if you go, yes, ax, yes, A-C-T-S. If you go the other way, why would you go the other way? All right, reference angles. Whenever I'm referring to a reference angle, it is always the angle that your terminal ray is making with the closest x-axis. So a reference angle, I kind of think of it as like a distance question. So reference angles are always going to be positive. The way the angle is drawn might be like a negative angle. But the distance from the x-axis to the terminal ray, we're always going to think of that as a positive number. So there's some boxes of formulas in your book about, like, if your angle shows up here, this is how you find, if your terminal ray shows up here, this is how you find the reference angle. But I find for most of us, if we just draw it, it's very obvious where the reference angle is and how big it is. It gets a little confusing when you're working in radians, though, because no one likes radians, but whatever, we deal with it. Quadrancials. Quadrancials are the special ones that occur on the x and y axes. So depending on where you are in the quadrantial, one part of your ordered pair is going to be 0, and then the radius is going to match the other part of the ordered pair, but you have to watch your signs. Like, for instance, if you're over here, this value is obviously a negative ordered pair for what you guys would consider the x value. They're calling it r here because of the way it's defined. All of this is like really obvious though once you graph it. So I almost hate to show you all those boxes from your textbook because it's just a lot of stuff that we didn't even bother putting on your formula sheet because no one uses it. You just draw it. All right, so we are going to be sketching these angles. I believe these are, yes, this is on your notes here. So 330 degrees. What you're going to do for me first is, of course, our initial side is the positive x-axis. We're opening 330 degrees in a positive direction, so you're opening counterclockwise. And if you think about your quadrancials, remember how this is 270 and this is 360? Whoops. So 330 degrees is going to land right there. But the important part is that you give me this directional arrow that shows me how the angle opened. You did a little bit of this on your homework on like the first book assignment maybe, or the second book assignment from your so far homework check. So the angle of 330 looks like that. What they want now is called the reference angle, which they use the alpha symbol. So the distance Remember, just looking for distance from the terminal side back to the x-axis would be how many degrees? 30 degrees. Very good. So reference angles are always positive because it's almost like they're measuring distance. That's the way I remember it. And then they get really weird right away. Negative 3 pi over 4. Well, that's a bummer. So some kids hate radian measures so much when they're drawing that they go ahead and they convert this to degrees. You're welcome to do that, but your answer for reference angle has to come back to radian. So you're going to do a couple of conversions if you choose that method. So you're welcome to, and I know you guys can do it fine, especially on your homework where you're not worried about how much time it takes you. But you can't do this without going that direction. So if you start at 0, obviously we're starting at 0, but this time I'm measuring a negative angle. So what if we measured backwards? What could I call this quadrantial down here if I'm measuring backwards? So if you back up a quadrant, that'd be like negative pi over 2. And then if I keep backing up, that's like negative pi. So negative 3/4 pi is going to be smack dab in the middle right here. And because we measured negatively, that's the directional arrow showing me how it opens. Now this is where it gets kind of crazy. I need the reference angle, which is the distance between my terminal side and the closest x-axis. So remember how this was negative 3 pi over 4, and this is negative pi. Remember, reference angles are always positive, so how much distance is between them? Pi over 4. Now, calculation-wise, basically you're subtracting those numbers. Distances to subtract. But because it's a reference angle, it's always positive. Always positive. All right, 9 pi over 6. Well, the first thing I'd like to point out to myself is 9 over 6 reduces. What's 9 over 6? Yeah, it's 3 over 2. This is actually a really easy question. Where's 3 pi over 2? So here's your initial side. Pi over 2, pi. This guy right here is 3 pi over 2. So there's your terminal side. And it opened positively, so your directional arrow looks like that. And then, because it's a quadrantial, there's no reference angle. Okay? Quadrantials are special, so you don't have to worry about reference angles on those. All right, next one. 11 pi over 6. You know what? Let's skip to... Well, we'll do the 2 radian ones. I'm going to skip the degree one because it's just getting boring. All right, 11 pi over 6. So if I want to think about... I don't want to have to convert every time, guys. I feel like it slows you down unnecessarily. So, you know, we got pi over here, 3 pi over 2. And this will come back to 2 pi. So 11 pi over 6 is just shy of 2 pi. It's one of your unit circle measures, isn't it? Yeah. So 11 pi over 6. And it opened positively, so I need to give a directional arrow that looks like that. Now the reference angle. How much distance is in between our terminal side and the nearest x-axis? Yep, it's pi over 6 away. Reference angles, always positive. They're measuring distance. All right. Yeah, okay, this is one of those weird ones. It's a negative radian measure. So for me, I don't like to have to convert back and forth. So I'm going to say, let's just call these negative angles so I can see where I'm at. This is negative pi over 2. This is negative pi. This is negative 3 pi over 2. And this would be negative 2 pi. So where the heck is 5 pi over 9? So what fraction, 5 over 9, just talk about that part. What decimal is 5 over 9 on your calculator? 0.5 repeating or something, isn't it? Okay, so it's over half. It's over 0.5. So, but it's not quite to 1, so it's somewhere down here. So now for my reference angle. Oops, wrong color. My reference angle is going to measure the distance to the nearest x-axis. So you need to find the difference between 1 pi and 5 pi over 9. So that would be 4 pi over 9? Okay. And the idea for reference angles, besides the fact that they're always positive because they're measuring that distance, they shouldn't be larger than a quadrant, right? So if they're larger than pi over 2, then you've done something wrong. Like probably your drawing has it landing in the wrong spot, so it's misleading you is my guess. All right. Easy peasy lemon squeezy. This is my favorite part. I think this is where like a kid who has a tough time with formulas, your teacher, really appreciates this part of math because there's a drawing that goes with it. So the formulas are almost like whatever at this point. So the formulas that we're going to be using, y over r over y, cosecant is r over y because they're reciprocal functions. Cosine is x over r. These are synonymous with your adjacent over hypotenuse, opposite over hypotenuse formulas. They're just simplified because when you get on to pre-calc and calc, no one wants to keep writing the little baby formula anymore, and they like to use the coordinate plane formula with the x, y, and r. All right, so they're going to give you an ordered pair, which I'm always going to draw it like it's a coordinate plane. I'm going to create a little triangle of sorts. And then finding r is going to be really obvious to us because it's just going to be Pythagorean theorem. And then once you have your x coordinate, your y coordinate, and your r, you could set up all these ratios. Now the example they did for you, notice all the ratios are reducing, so you have to worry about that. So basically everything you know about math, just don't forget it. All right, here we go. If I was to plot 2, -5, just like in a coordinate plane, that would be like here. And I'm going to create a triangle with the closest x-axis. Now I know it's not proper to call a leg of a triangle -5, but I'm going to write it as -5 anyways because it's going to help me when I write my ratios. So there's your x, there's your y. I need you to find r. So it's 2 squared plus 5 squared. Notice this time I didn't write the negatives because I'm squaring it, so it's negligible. What is that, the square root of 29? Okay. So they want me to write, I'm guessing the 6 trig functions. Yep, here we go. So we have sine theta followed by cosine theta. Nope, let's do cosecant. And we have cosine followed by secant. And then, whoops, tangent, followed by cotangent. All right. On that triangle, if you got in a jam and you forgot your x, y, and r formula, just remember theta is synonymous here today with the reference angle, this angle over here in the corner by the origin. So you could go old school and you could do the opposite and adjacent and all those little baby formulas. But it might help your brain if you try. If you're good at memorizing formulas, just hurry up and memorize them. Sine's easy, right? Y over r. So the y coordinate is -5. You just found the r coordinate to be square root of 29, and then you go, oh, that's sad. Tell me why. Can I leave my answer like that? Apparently not. All right, so -5 square root of 29 over 29. So just like in a previous lesson, when I have you do the reciprocal function, choose wisely. Don't reverse this fraction because you're going to have to re-rationalize. Reverse this fraction. So negative square root of 29 over 5. The negative can go anywhere in your fraction, numerator, denominator, or out in front. Cosine is x over r, so that would be 2 over the square root of 29, which will come out to 2 square roots of 29 over 29 when you rationalize. And then again, choose wisely when you go to flip it around. We got square root of 29 over 2. And then tangent is y over x. So we have -5 over 2. Don't have to do any work on that one. Cotangent, just flip it around, -2 over 5. What do you notice about the signs of your 6 trig functions here? Who's positive? Cosine and secant, his buddy. What quadrant are you in? Quadrant 4. Should that have worked out that way? Is that the quadrant where cosine is positive and the other ones are negative? Yeah, perfect. Okay. So that's a nice little double check. Like, you could imagine if you graph this in the wrong quadrant, you're going to be in trouble. All right, so I'm actually going to skip that next one. These are kind of boring, so, if you don't mind. All right, let's take a look at, we warmed up, right, with the 30, 60, 90 stuff. So if you, I think they're on your paper already, the 30, 60, 90 and the 45, 45, 90 formulas are there. The book that we stole this out of, instead of x times the square root of 2, they write it as square root of 2 times x after it. The important part is x is not in the radical. I don't like that notation, so I'm going to scrap that. Which means I'm also going to scrap this one to say x times the square root of 3. So, technically, you can develop all those unit circle functions by using 30, 60, 90s, but we've already discussed, like, there's not enough time to do that on your unit circle quiz, so you guys are just memorizing. And we are going to be finding the exact value of each expression using special right triangle relationships. Okay, there's a couple of questions like this on your summative, and then after this point, pretty much we're going to be using the unit circle to investigate things further. So suffer through these couple with me and then you'll be all right. Sine of 5 pi over 3. So they went ahead and drew it for us, and I don't think that's on your paper, so go ahead and sketch something that looks like this out for you. This is where 5 pi over 3 would have landed in the terminal side. And then they created a triangle with the x-axis. So here's what we'd have to figure out. If you're using right triangle formulas, you'd have to figure out what kind of right triangle we're looking at. Now, bless you, Hofbauer, she even gave me like a mostly to scale right triangle. I think what I might do is go ahead and convert these to degrees. Unless you know it off the top of your head. Anyone know what 5 pi over 3 converted to degrees is? It's a special one, but it's okay if you don't remember. It's 300 degrees, okay. Which means how big is this reference angle? It's a 60 degree angle right there. So, surprise, surprise, you have a 30, 60, 90. There's a couple of different ways to do this. On the unit circle, the radius is always 1. So there's no shame in doing it that way. The problem, however, is if you call the radius a 1, the hypotenuse, what do you have to call this little leg here? If you think about the 30, 60, 90 triangle, isn't he half of the hypotenuse? So you'd have to call that a half, and then this leg is going to be called half times the square root of 3, better known as square root of 3 over 2. Now, I'm going to claim that we're not technically correct, and this is going to feel weird because you don't usually label triangles with negative legs. I think one of these legs is negative. If you think about the direction at which you're traveling, the half is positive, but the down leg here, that's a negative leg. I know it's not mathematically proper to call a leg of a triangle negative, but because we're working in the coordinate plane, we have to consider signs. If you don't like that, sometimes when I teach this, I tell the kids to call the x leg a 1, and then call this a 2, and then call this a square root of 3, and then you can set up your sine ratio just based on the sine formula that we just learned, the y over r. You have to do a little rationalizing sometimes, but it's okay. Anywho, guys, do you remember the sine? Again, y over r is fine. What would be the sine ratio here? If it's y over r. Negative square root of 3 over 2 divided by 1 technically, right? Do I have to divide by 1? No. So this is the benefit. If you call the radius 1, because that's what the unit circle does, then you don't have to divide by r ever. It's really quite a boring question at that point. The other thing you can think about, do you guys remember when you're on the unit circle? And this only works for the unit circle. You guys have this xy ordered pair of 1/2 comma negative square root of 3 over 2. Do you remember which part of the ordered pair is cosine and which part's sine? This one's cosine and this one's sine. So all these kind of ideas are coming together right now, and it all revolves around the unit circle. So if you just want to have like one thing in your brain right now and just the unit circle, that's fine. All right, this one, 210. Already drawn for you. Thank you, Hofbauer. I need to know what angle we're working with though here, guys. What is the reference angle here? If it's 180 to 210, that would be a 30 degree angle. So that's obviously a 60 degree angle over here. So we have another 30, 60, 90. Do you want me to do this one where I don't make the radius 1, or are we comfortable with that? How did you guys do it in trig? Did you always make the radius 1? You don't remember? Okay. I think she does, so I don't want to mess with anyone's brain right now. Do you want me to show you the other way? I can. It's not any easier, frankly. It's just a little different. All right, so if we call the radius 1, that means your little leg is going to be called 1/2, but look how this little leg is moving. It's moving downwards. So I need you to call that a negative 1/2, please. And then this medium leg would be negative 1/2 times the square root of 3. So negative square root of 3 over 2. So have you caught on to what the legs are on a 30, 60, 90? They're the same every time. Okay, you just got to watch your signs. Again, I know it's not, probably Hofbauer's going to yell at me for calling those legs negative, but it's just, it helps me. I forget about signs if I don't do it that way. All right, guys, cosecant. Cosecant, you can think of it as a reciprocal of sine, or you can use your new formula, which is r over y. So this time, r over y, oh no. Guys, how do you divide fractions? Don't you multiply by the reciprocal technically? So what you're really doing on this fraction is you're taking 1 and you're multiplying it by the reciprocal. And your math teacher, whoops, is not going to like you saying it's negative 2 over square root of 3. What is your math teacher going to want you to do? Rationalize it, so it's negative 2 square root of 3 over 3. That was my answer. I kind of wrote you a big old maze there. Whew. All right, number 11. Already drawn for you? Thank you. And then I need to know how big this angle is. Thank goodness. We finally got a 45, 45, 90. So this is a 45-degree reference angle. So yes, it's a 45, 45, 90. So the hypotenuse, if you want to call it a 1, like it is on the unit circle, that's fine. But it does kind of give you a bit of a challenge here for the legs. Because the legs, if you think about the special right triangle formula, 1 is supposed to be the leg times the square root of 2. So if you solved for x in this equation, you end up dividing by square root of 2 and then rationalizing. And look at that. What do you get? Square root of 2 over 2. Now, because of the first quadrant, nothing's negative, so I don't need to worry about doing anything there. You guys already know the unit circle, so I feel like when you hit a 45, 45, 90 or a 30, 60, 90, you kind of know what the legs are going to become, so just kind of fill them in. And like I said, I know it's not proper to put negatives where they're not supposed to be, but put them anyways. I need the cosine, so you can either use your new formula of x over r, or you can just say, I know that this is going to be the cosine because it's a unit circle. And the answer is square root, of 2 over 2. Now that's us developing, but notice every single question I just gave you was one of our special angles off of the unit circle. Guys, are those the only angles that exist?
Yes.
If only. No. So like what if I said, you know, figure out something that's not off the unit circle? We would just skip it, of course. Now, so on your test, there's a question where, yes, it might be from the unit circle technically, but in the instructions of the section, it's going to say, use your special right triangle patterns to figure this out. So humor me and use your special right triangle patterns, even though you know you have a reference page right next to you that says, hey, I know what the secant of 30 degrees is because I could just look at my unit circle, okay? So humor your teacher. What do we got here? Are we done yet? Are we done? No, we're never done. All right, this is what you've all been waiting for. Because the unit circle is all ready for you. If I happen to give you stuff that you could reference on the unit circle, you just got to reference the unit circle. So, remember the ordered pairs on the unit circle. The xy ordered pairs are really cosine comma sine. I don't know if that's anywhere on your reference page, but I feel like you guys don't need that because you should have that memorized by now. So when I start asking you things like, where are we at here? These questions. Like, what's the tangent of 5 pi over 3? Well, here's 5 pi over 3. Where are you at? If this is cosine and this is sine, and I'm supposed to find tangent, there's a couple of different ways you can do this. Remember, the formula for tangent from today was y over x, but knowing that the xy ordered pair is really cosine and sine, do you guys remember there's a formula for tangent that says it's sine over cosine? That's one of your trig identity formulas that you would swap out a bunch. We're going to get back to that unit next, don't worry. So using one of these formulas to find the tangent ratio, that's kind of annoying. So can you guys please write down on your paper, because I'm going to ask you in a minute and I'm going to forget by the time I get there. Write down this ordered pair. So 1/2 comma negative square root of 3 over 2. Oh, dang it. It's there. So when I go to find tangent, if it's y over x, that means I set up a little fraction work here, so negative square root of 3 over 2. And then instead of dividing by x, I could just multiply by the reciprocal. There's your tangent. I would say the reciprocal functions are the ones that get us in trouble just because of manipulation. And of course, no one likes fractions. Oh, that's nice. Look how wonderful Hofbauer is. She gave me a whole unit circle over here. All right. First one should be easiest question on the whole page. Cosine of 7 pi over 6. That's like, look on your unit circle. Boom. Which one's the cosine? The first ordered pair coordinate, so negative square root of 3 over 2. The secant of, okay, this one's a little challenging. Negative 3 pi over 4. Remember how we can measure negatively if you want? So if this is 0, this is like negative pi over 2, and this is negative pi. So negative 3 pi over 4 is right here. If you didn't like doing it that way, feel free to convert or at least find a reference angle. I don't care. But the secant, guys, we don't actually have secant. We have cosine and sine, but who's the reciprocal of secant? Cosine. So if you take your cosine, and after you do a few of these, you probably recognize there's a shortcut here. If you take the cosine and then you re-rationalize it, flip it and re-rationalize it, what happens? The 2's cancel, but you still have negative square root of 2. That's that answer. And then tangent of pi over 2, so we're talking up here. Remember, tangent is y over x, or you could say it's sine over cosine. So using that formula, or one of those formulas, you get, 1 over 0. What's that? That is undefined. Yes, if 0 is your denominator, that is an undefined expression. What if it was the reciprocal of that? What if it was cotangent? That would be 0. Very good. 0 divided by 1 is 0, but 1 divided by 0 is undefined. All right, so those are actually really easy questions that we're going to be throwing at you. Your homework looks like it's a gazillion questions, but a whole bunch of them are just that. Like, look at your unit circle and fill it out. So, obviously the reciprocal ones, the negative radian ones, those are the more challenging ones. You guys have page 251 being assigned to you now. And I think that's actually, is that the last item on your homework check? You're in good shape. All right, good luck.